As you know, I had some issues with the computer yesterday, and so that precluded my ability to do the live version of the course. Then so let's go ahead and let's go ahead and do the right now. Okay, so let's talk about linear regression analysis. So this is actually quite a simple lecture. It's not a very long one. Linear regression analysis is a way of making a prediction. We try to predict because prediction allows us to plan ahead in many different ways. In public health, we try to understand what predicts certain disease outcomes. However, in other fields, regression is used to predict sales or wins and losses. There's so many different ways regression can be used. What we're talking about today is linear regression analysis. And in this specific type of analysis, we're looking at continuous outcome variables. So that's our goal here, is to predict some kind of continuous outcome variable. If we had a discrete variable, we could use a logistic regression, which we're not covering in this course, or we will, I think, later in the course. I believe later in the course. We're not covering right now, though. Okay, so that's more of a non-parametric issue. Non-parametric means when your data are not normally distributed. We call those non-parametric statistics. So simple regression is a type of regression when you have one predictor variable and one outcome variable. Last week we did correlation analysis. Correlation analysis just looks at how the two variables move in relation to one another, right? So if one increases, the other increases, or one increases, the other decreases. That's what regression does, but there's no model making any prediction. It just talks about the extent to which the two variables co-vary. They vary together. In this case, though, we are making a prediction, and this prediction is a line. So if you look at this first equation, the prediction equation, first of all, I put a little hat on the y to indicate that it's a predictor. Anytime you see a hat on a variable, it indicates a predictor. We have the I here indicating that this is each individual's prediction. So like, for instance, if I was trying to predict the amount of sales a store makes on a given day based on one predictor variable, this would be sales, the predicted sales. This is a line, so like every line, there's an intercept where the line crosses the y-axis, and there's a slope to the line. It's a gradient. Slope, if you remember from early math, is rise over run, right? So the change, what happens for one unit change in one direction, like in the x, the x-axis, what happens in the y-axis. The b here, b1, in this case, is the slope that relates this predictor variable x1 to the outcome variable. And you notice that x1 is a specific predictor, and I labeled it 1 because there's only one, meaning there could be more than one, and the I means it's an individual. So each individual has a score on the x variable and a score on the y variable. You'll notice that the b0 and the b1 do not have i's by them. So that means that they're not individually based. They're based on the entire population. So they're predictors. They're what we call parameters, population. Remember we said statistic versus parameter. So they're parameter estimates of population parameters. Multiple regression, we add more predictor variables. Generally, it's not enough to make a prediction based on one variable. And we can actually judge that by looking at the R-square. If you recall, R-square from correlation is a proportion of the shared variance between two variables, and I had mentioned that we use that in regression. So it's a proportion of the variance in the outcome predicted by the predictor variables. And it can range from 0 to 100%, right? So here we add variables to try to enhance our ability to predict our outcome. So we have b1, x1, each one has its own slope, right? And it can go on until, I don't know how many, but you don't never really want to have too many predictors, because then you start losing value of your model, just starts losing its efficacy. So you may be wondering, or at least I was always wondering, I always wonder everything, how are these slopes related to correlations? Well, here this equation shows you how a slope, and here now I use a generic b rather than b1, b2. I just use a generic b. It's related to the correlation between two variables. So we're looking at the example of simple regression. The correlation times the ratio of the standard deviation for the y variable to the standard deviation of the x variable. So you have to be able to create this regression model by hand if I give you specific information. So I rewrite this prediction equation as follows. I change the B0 to A, and I change the B1 to just a generic B, right? So now we have Y sub I, so that's our predicted value of our outcome variable. By the way, some people will say dependent variable, some people will say criterion variable, some people will say outcome variable. For the predictor, they'll say predictor, independent variables. Just be aware that there's many different ways to say these variables. So if we rearrange this equation, we get A equals Y sub I minus BX. So the best predictor of any variable in the absence of any information is the mean of that variable. So that's why we substitute the mean here. This is all we have, right? So let's go ahead and here I just show you how I derive it. So that's that's what I just mentioned there. All right, let's go ahead and do one for example. So we come up here with, if we get the Y, we get the A and the B, we can create the equation. That's all I wanted to say there. So here's an example. Write a regression equation for the following data with per capita consumption, cigarette consumption in 1930, predicting incidence, new cases of lung cancer per 100,000. Also interpret the effect. Means, so you get these data. Mean cigarettes is 603.64 per capita. Right, in 1930, a lot of cigarettes. Mean lung cancer cases was 20.55 per 100,000. Here's your standard deviation for the predictor variable, right? So cigarette consumption and standard deviation for your outcome variable, cancer. And here's the correlation between the two. And here are your data. So this again, 1930, it was a long time ago. People used to smoke a lot more. They don't smoke, well, they still smoke, but different kind of cigarettes now. So let's go ahead and do this. So we need our slope, our B is called our slope. So we look at the correlation times the standard deviation, quotient of the standard deviations, right? And we get correlation is 0.737 times this ratio here. And we get 0.0228, so that's our B value. Need to calculate our intercept. We did use the equation I showed you earlier. We substitute the means in where applicable, and of course the B value, and we get 6.787. So then we write our regression equation out, and so you have to be able to do this. Let me repeat that, you have to be able to do this. So it's 6.787 plus 0.0228 times cigarettes. So we can get, put a little I here. Cigarettes, I. There you go. So we get this equation for save that. We get that equation then for predicting what cancer per 100,000 is for a country. That's what this is giving. So it's going to give us for a specific country what the predicted value of cancer, lung cancer per 100,000. So if I plug in the number of cigarettes per capita, that's what I'd get. So how would I interpret this? So each additional cigarette smoked per capita or per person in 1930 was associated with a 0.0228 increase in the incidence of lung cancer per 100,000 people. That's the interpretation. You have to be able to interpret that too. It's an increase because this is positive. It's not a decrease. If it was a negative, it would be a decrease. All right, so let's do this one. Using the table below, write the regression equation to predict physical activity support from physical activity enjoyment. Okay, let's do that. Okay, and here's the correlation. So notice the way I give you these data. Let me see if I can find those. Ah, yes, if I can find those data. Hold on a second. Let me get what I need here. Close and oh boy, let's see, show all. Where did I download that? Here it is. All right. So I am using the same process here as I did before. Sorry for the bad notes. Usually I like to make them look a little prettier, but you know, again, I didn't have my computer last night, so did the best I could. All right, so here's the form of the predictor equation. You have the outcome variable with the hat on it. It means predicted, the intercept, the slope, and the predictor variable. We take the correlation between the two. So let's take a look at that correlation matrix here. So this is the correlation matrix. This is your prototypical correlation matrix, right? SPSS provides you additional information, whether they're significant, the sample size involved. But here's the Pearson correlation between the two. It's 0.432, and it's very significant. You can see here at 0.01. So it's 0.432, so I plug that in here, 0.432. We need the standard deviation of the outcome and the standard deviation of the predictor. And of course, I gave you that as well here, right? They give you the means and standard deviation. So you need all this information, right? This is the standard deviation of the outcome is, oh, it's wrong. Wait, this is the wrong one. This is the wrong one. Oops, let me pause for a second, apologize. I was right, I don't know, I was just, I started reading something wrong over there, yeah. So here's our means and standard deviation. And I'm sorry, we're predicting physical activity support from physical activity enjoyment. My apologies. So physical activity support, this is your outcome. So this is the standard deviation of your outcome, and this is the standard deviation of your predictor. Okay, so be wary. Sometimes I will give you variances rather than standard deviation. You know that the standard deviation is the square root of the variance. So I might trick you that way. So use your heads when when you're dealing with my exams, because I do that stuff on purpose. All right, so where are we? Here we are. So it's the ratio of the y variable to the x variable. Make sure I have the right. Let me just make sure I have everything right here. So it says regression predict physical. Yes, we're predicting physical activity support. So the idea is that if people enjoy physical activity, they'll get more support from their parents and friends to be physically active. Okay, so let's go back here. And we just basically, once we get this b value, right, it's 0.208, we plug it into the equation. We have the means of each variable in that first table. Mean for each variable is here. We have the standard deviations. We have every single thing that we need to complete the problem. Okay, so it's not a lot of work then. You just need to plug things in where they belong. And we get our final regression equation. So you have to be able to write it out. It has to look just like this, with the eyes, with the hats, with the x, with the I, intercept and slope. How would you interpret this? Each unit increase in physical activity enjoyment results in a 0.208 increase in PA support. Again, it's positive. By the way, this unit increase thing, you have to know what your units are. That's really important. Physical activity support and physical activity enjoyment may be in different units. Like, what I mean by unit, they could be, one of them can range from 0 to 100, so a 1 point change is a 1 unit change, right? But the other could be ranging from 0 to 10, right? So that, you know, they have to know the units whenever you do regression analysis. Let's talk a little bit about regression assumptions. Since we're starting to move, we really want to move into multiple regression analysis, because generally one variable is not enough to make a prediction. So here's some assumptions. The relation between the predictor and the outcome is linear. That means it's a line. It's not curvilinear. It doesn't look like like an inverted U, or it's not like a sine wave where it goes up and down, up and down. It's linear. Now, it doesn't have, you can make regression with curves, but that's a little bit different. We could talk about that in a more advanced course. Observations are independent of one another, so there's no dependence on observations. Normality for your residuals at each level of x. So when you make a prediction, you're going to predict the outcome variable, but you're not going to do it prediction, right? That's what the R-square is about. It tells you how much of the outcome variable is predicted by your predicted variable. Let's say you predict 20%, right? Well, percent can only go up to, percent means per 100, it can only go up to 100. So if you predict 20%, that means 100 minus 20 is 80%. 80% of the variance is left unaccounted for. That variance is shown in a residual, right? The residuals are supposed to be independent and normally distributed. I'll show you what that means in a second. And that their variability is supposed to remain constant across different levels of your predictor variable. Again, I'll show you in a second. In fact, here it is. So here's your line predicting, or x predicting y, and you'll notice that these are the residuals. So this is the distribution of the residuals, right? It says distribution of y. Well, you know, we don't have a y anymore because we've already used it in our model. So what's left over is what we look at, the residuals. They should be normally distributed, okay, across different levels of x. And the variation should be constant. So just let's make pretend that this is, well, this does show the variability, right? Because it shows standard deviations from the mean. They should remain constant. It should be like a tube, right? With parallel lines showing the distribution. So we talked about the interpretation. When we're doing multiple regression, it's not enough to say each unit increase in x results in a b change in the outcome. We have to add holding all other variables constant, because when we look at multiple regression, we evaluate the predictors for significance. Our null hypothesis is that the predictor, the b value, the slope, is equal to 0. Like there's no effect of the predictor on the outcome. Our alternative is that there is some kind of an effect. But when we evaluate it, we evaluate each one variable at a time, assuming that we're holding all the other variables constant. What I mean by holding them constant is everybody's given the mean value of those other variables. All right, so let's do an example. Using the data in regression.sav data set, so you need to do this because this is what your next SPSS assignment is going to look like. Using the data in the regression.sav dataset, conduct a simple regression analysis, predicting physical activity support from participant biological sex. Okay. Conduct a multiple regression predicting physical activity support from biological sex and physical activity enjoyment. Okay. Interpret the results. So before we go, well, actually, let's just go ahead and do that. Let's just go ahead and run it first. So they said here, let's analyze regression, linear regression. The first step we want, see again, we have our variables listed here. I like to right click them because I kind of know what the variable names are. So we want to predict physical activity support. That's our dependent variable from biological sex. In this case, it's written as female. Why? Because this is just my personal preference. If I know male is 0 and female is 1, why not just call it female? Let's just make I'm going to do a couple minor things here and I'll explain them as we go. Statistics. I always like to have confidence intervals. There's no need for R-square change because R-square change is a statistic we look at when we look at change in the R with the addition of each predictor. We'll talk about collinearity in a moment, but we don't need that now because collinearity is correlation among predictors, and there's only one predictor in here. Descriptives, I'm not going to put that in here because sometimes it gives us misleading information. I mean, it gives us the mean of sex, and there is no mean. It's just either 0 and 1. I will add this Casewise Diagnostic. This is telling me if there are any weird cases in there. Like, for instance, it could be a data entry error. I look for weird cases. If there's 3 standard deviations away from the mean, you should know based on the 68, 95, 99.7 rule that anything that's outside of 3 standard deviations from the mean has a very small chance of occurring. So it could mean that there's a typo or something like that. And did I do plots? I want plots, yes. I'm going to talk about this. Well, actually, I'll talk about it right now. We plot the residuals, right? Because I mentioned the residuals should be constant across different values of a predictor. So let's do that. Let's put the z residual. So this is basically our indicator of y, and our z predictor Z means they're standardized. They're Z-scores, right? Okay. And we should also do something called normal probability plot. I'll talk about what that is. Hit OK. Here's your example of simple regression. It says what variables in the model. Here's your dependent variable. Has support for being physically active. Just a way to check that you did everything right. According to this, sex accounts for 0.018. Multiply this by 100, 1.8% of the variation in our outcomes. So it's not that much. The model itself is significant. You'll notice that this is an F table, like you have an ANOVA, right? Exact same table as you have in the, exactly the same as in the ANOVA table. And this model is significant, although that doesn't really mean much to us. In this case, it's okay because there's only one predictor, but this doesn't really tell us much. What we really want to do is look at and see if the coefficient, the slope, is significant. So here we see that this p-value is 0.000, so this is highly significant. So in other words, being female influences physical activity support. Now if I wanted to interpret this as a 1 unit increase in our predictor variable, well, there's only 2 levels of our predictor variables, male or female. So male is 0, female is 1. So 1 unit change means being female versus being male results in a 1.355 decrease in physical activity support. In other words, females get less physical activity support than males. Here's your confidence interval. I'll talk about this standardized beta in a moment. We'll look for residuals, anything weird here. Let's take, I don't really see anything weird. We have to look at each case by case. Regression standardized residuals. This isn't a very good picture because our predictor variable predictor variable. It has only 2 levels, but they look pretty constant across the 2 levels of our predictor, right? That's what I'm looking for, is constancy. And this is what we call a PP plot, a probability plot. It maps the expected probability distribution, which is normal because our residuals are supposed to be normal, versus the observed differences. There's a straight line that runs through here. If we do a really good job predicting, so in other words, we have a normally distributed residuals, these points should fall right on the line. If they go away from the line, that means there's some deviation from the predicted value. We can look at that. I'll add another graph to it to help. Okay, so now the next step is to analyze. We run it again, but we're supposed to add something else. Let's see, what is our instructions? Conduct a regression. Let's see, what was the next step? Conduct a multiple regression analysis predicting physical activity enjoyment. Okay, we did that, and physical activity enjoyment. Okay. So this is actually the only one. This is a mistake, so I'm going to delete this. Okay. All right, so we add physical activity enjoyment to this model. So now we're going from simple to multiple regression analysis. Okay. So it's analyze, regression, linear. So you'll notice now it says next here. And you don't have to do this, but I do it because it actually, and this is what I want you to do in your homework assignment, right? But one doesn't truly have to do this, but in your homework assignment you do. I'll say enter this in the first step. So that's, see, it says block 1 of 1. So I'm going to add a new block. And here I'm going to enter, what did I say I wanted? I can't remember what I said. Physical activity enjoyment. Okay, so we add physical activity enjoyment. Let's see. I think that's paces. Okay, physical activity enjoyment. Enter. All right. So now I have 2 variables in the model, so I can go back and add Collinearity Diagnostics. This tells me whether or not the two variables are highly correlated. Actually, I should add some. What else did I want to add? Continue. There was a thing with plots I wanted. Yeah, I wanted the histograms as well. Continue. Everything else stays the same. Options. We got that. All right. So now we have our model ready. Now you'll notice it says method. And there's stepwise, remove, backwards. There's actually some methods that will do all the work for you, which is decide which is significant and which is not, and just remove and add and remove and add. I don't believe in those, so that's why I don't teach them. I believe in you knowing your field. You pick the variables that you should pick based on your knowledge of the field. So I refuse to teach you about those fake canned methods. Hit OK. All right, let's do, ooh, look at this. Things look different now. All right. Okay, here we are. So now we have two models. One has sex by itself, and the other one has sex and physical activity enjoyment in it. Dependent variable remains the same. Notice how this model summary table now includes two values, right? Two models. Model 1 accounted for 1.9% of the variation. This new model accounts for 19% of the variation, so we did a better job. By the way, there's an adjusted R-square versus an R-square. The R-square is used to predict the proportion of the variance accounted for by the model. This adjusted R-square takes into account model complexity, how many variables you have in there, etc. And it's a better way to predict how well your model will make a prediction of the population values. Here you have your ANOVA table, but now you have two tables. So really the second one is the one we're more interested in, because we're not interested in the first one. The first one was the one only including the first predictor variable. We're really interested in the total model, but it's significant. But now that we have two variables, the ANOVA table becomes less important in general. What's important is this table right here. Again, you have to present both of these, model 1 and model 2, but I'm really interested in model 2. Right, because this is the one that, see, we controlled for sex because there are differences, sex differences in things like support for PA. However, what we're really interested in is knowing whether physical activity enjoyment has an effect above and beyond the effect of sex. Right, so let's take a look at it and look at significant. Significance changed a little bit for sex here. So physical activity enjoyment has a significant effect. So how would I interpret this? Each unit increase in physical activity enjoyment result in a 0.201 increase in physical activity support holding sex constant, right? We have to say holding sex constant. Now here's the interesting thing. For the first time, we're going to interpret the standardized results. Standardized results are done in standard deviation units, so they're actually directly comparable. Whereas I cannot compare these two directly because they're based on the units of measurement. I can compare these two directly. So 0.419 is a lot stronger than minus 0.07. Forget the sign, but look at the absolute value. 0.419 is bigger, right? So that means physical activity enjoyment has a bigger effect than sex does on support. So that's what this is telling me. But I can't determine this here. Impossible. But here I can. So how would I, let me show you how I'd interpret this in terms of standardized values. So this, you have to know how to do this as well. A 1 standard deviation unit increase in physical activity enjoyment results in a 0.419 standard deviation increase in support. Now, interpreting this one is a little bit different because, see, we don't talk about standard deviations when there's only two values. So when you have a categorical predictor variable, this is what you'd read. Being female versus male results in a 0.07 standard deviation decrease in physical activity support. You see the difference? And we see our confidence interval. Oh, our confidence intervals here, right? They don't cross 0, right? Collinearity diagnostics. Let's go back and talk about those really quickly. So Residual. So what is a residual? The residual is the difference between the predicted value and the actual value. That's all a residual is. So we take the predicted value, subtract the actual value for each individual, and that's why there's an I there, and we consider those residuals. Any residual that's greater, I determine any residual that's greater than 3 standard deviations from the mean is considered an outlier, and we need to explore it. Doesn't mean we need to remove it. We just need to explore it because it could be a data entry error. Like somebody's weight, instead of 100 pounds, one could have entered by accident 1,000 pounds, right? So it might just be a data entry error. Multi-collinearity looks for the correlation among the predictor variables, and there's 2 measures we use for that. There's the VIF and tolerance, the variance inflation factor and tolerance. So tolerance is the proportion of the variance of a predictor that's not accounted for by the other predictors. So we'd like the tolerance to be really high, right? So we actually run a regression among the predictors for each predictor being predicted by the other predictors. So we want the proportion accounted for, not accounted for, to be very high, and the proportion accounted for to be low. So that's tolerance. So values of tolerance less than 0.1 are troubling. It means over 90% of the variance in that predictor is accounted for by the other predictors, and tolerance is VIF is just the opposite of the reciprocal of tolerance, 1 over tolerance. I told you about this. Well, let's take a look at these. I already told you about coefficient of determination is just another term for R squared. All right, let's just take a look at our results here. Okay, so we see that here's our tolerance in VIF. Tolerance is very high. That means 98% of the variance in each of these variables is not accounted for by the other. And then VIF is good too, right? 1 divided by tolerance is VIF. It always gives you this excluded variable, like what would happen if you add the like in Model 1 doesn't include physical activity enjoyment, so what would happen if we added in? It's not that important for us here. Let's look at collinearity stuff. This you can kind of ignore because this is a little bit beyond the scope of our text of this course, but you can do a diagnostic for each of these variables. Here, in terms of standardized residual, see case 1409. So this is individual 1409. Has a standardized residual of 4.753. So that's really big. So see, it has 25 for physical activity support, whereas the predicted value is 3.51. So the residual is 25 minus 3.51, and it's pretty large. So this could be a data entry error, or this person could have just put, marked all 5s if the scale is 1 to 5 or something, like just not even paying attention, just marked everything. So that could be one that I could get rid of, but it's only 1 out of a lot of people, so I probably wouldn't get rid of it. Here's a histogram of our residual. If you look at this, it's really nicely. It looks nice. It looks very normal. It's a little thin, so this kurtosis might be an issue, but you can translate this to this PP plot here, and most everything's directly on the line, which I mentioned, so it does look quite normal. I mean, right here in the center, there's some deviation, and that may be because of this thinness of this line, right? Because there's a lot. It's very concentrated around the mean, but that's not a bad thing. Oh, this is what we talk about residuals being constant across different levels of the predictors. The more predictors, the better this graph looks. But if you think there being a line right down the center, this is as constant as you can get, right? So there's no change. Basically, there's no change in how well the model predicts the outcome for different levels of the predictor. That's what this is saying. This is the predictor, and this is the outcome, and they seem pretty constant, right? That's it for us for today. Study this up so you can be ready for the exam. Thank you very much.